In this video, we'll be observing something termed magnetic induction and describing what it is and how it works. And in order to do so, we'll talk a fair bit about magnetic flux. Now, let's just start out by watching a couple of interesting videos where we'll see some phenomena we haven't seen before and may appear a little odd. Now, in this first video, we're going to observe something fairly simple. Somebody's going to drop a magnet through a copper pipe. Now, copper isn't a magnetic material, meaning if you tried to stick a magnet to it, it wouldn't stick at all. It'd be the same as trying to put a magnet up against wood or any other material. So there's nothing in terms of magnetic forces, the usual magnetic forces that you're used to, that's going to go on here. It would just act like any other type of material. Now first he's going to show you what happens if you drop a normal object. Here's an iron ball. Nothing special about the iron ball. It's just a regular object, falls straight through. There's nothing in the middle on that tube. And if you drop a magnet, though, it takes a lot longer to fall through the tube. A lot longer. So what's going on? Let's take a look at this from the top, and you can see that nothing's touching it. It's freely just floating down at a far slower speed than normal. Which is kind of weird because there's no normal magnetic force that you're used to. That thing is not acting like it's a magnet in the sense of it's not something like iron where it's sticking to the sides. You can see that because it doesn't actually touch the sides. It's almost as if it just has a big drag, but air resistance wasn't causing it. It's something the same size. The iron ball fell through just fine. This is something new that has to do with magnetism. Now the next video I want to show you is a little bit less clear in how it works because this will be looking at alternating current, which is a type of current we have not used before where the direction of the current switches back and forth. So some of the details about what it's going to show here might be confusing, but the basic principle is going to be something important. And it won't appear initially that it's tied at all to what you saw with that magnet being dropped down a copper tube. However, it is actually the same phenomena. So here's what we're going to do. We're going to have a loop of wire, and this is simply just a wire looped around a frame that supports it, and there'll be we're going to hook up a light bulb to this. And then what they're going to do is just take this light bulb and light bulb hooked up to a wire that's wound around and put it near another source of current, another looped set of wires. These are, I guess, technically both solenoids. And place one over here. And here we have just a piece of iron to make this a stronger magnet by sticking iron in the center. And then they're going to run current through the wire. That'll make it act as a magnet. And we're going to stick this onto here, and note there is no battery involved in this circuit. This circuit is simply a wire with a light bulb in it. And as you can see, it doesn't light up. But if they place it nearby the other magnet, it lights up. Even though there's no battery involved, it lights up. So here what we've seen, and this is a little bit a dark version so you can see it a little bit more clearly, is some new source of current that's not from a battery. It's acting like a battery in the sense that it's running current, but it isn't a battery. Now, this is alternating current, so this is not as clear. The qualitative effects about when is it bright do not match fundamentally what's going on. One will be a little bit less showy of a demonstration, but more clearly understood and more clear to what we'll be describing as the reason why this is lighting up will be more easily shown in the next video. Now, this video is a lot more showy, a lot less showy, excuse me, but it's a lot more clear about the cause. So here what I'm going to do is again we're going to have a magnet involved. In all three cases, we had something that was acting like a magnet. The first case, we dropped down the copper tube. It was just a type of a bar magnet that was shaped as a sphere. In the case of the second one, it was a solenoid that was making a magnetic field. It was doing strange things because it was alternating current flowing through it, which we won't talk about until the next chapter. Here, what we have is just a north-south baromagnet, which we're just going to stick into a solenoid. Okay, so this is again just wrapped pieces of wire that they plugged into something that measures the current. Positive, if it deflects to the right, it means the current's running in one direction, and if it deflects to the left, it means that current is running in the other direction. And there is no battery in this loop. So everything we know so far says no battery means no current. So let's watch what happens to the current. Note a few things about this. A is not staying on zero. That means that the current is non-zero when it gets pulled. It also keeps being pulled one way versus the other. Okay? So note that as you go in, it goes to the left, and as you go out, it goes to the right. So there's currents that are alternating in the direction in which they flow. One times go one way, one goes the other way. Now also note that while they just hold the magnet in there, there was no current. Watch, let's look at this again. So while it's just being held in there for a few seconds, and I'm pausing it while it's being held, so you can point out that there's no current. In the center is where there's no current flowing. So it's not whether or not there's a magnet in there. In other words, it's not because there's a magnetic field in this area by the wires. It's only when the magnet moves, so the magnetic field changes from one situation to the other. And it depends on how it changes. Being put in versus being put out changes whether it gets pulled to the right versus being pushed into the left. Okay, meaning current flows one way versus the other. Also note, if you switch the direction in which the magnet is facing, you end up having the opposite deflection types. Now pushing it in deflects to the right, and pulling it out deflects it to the left, which is opposite of how it was before. And again, he's showing that if you just leave it in there, nothing happens. It doesn't matter which direction the magnet is facing. So this is ultimately why the light bulb lit up. It was because there was current flowing. That's what was kind of the easiest way to see that there was current flowing. But this little ammeter here, right here, is also showing us directly that current is flowing. So this general phenomena is referred to as magnetic induction. And the basic idea with magnetic induction is that changing magnetic fields acts like a battery. Okay, we've seen it act like a battery to light up a light bulb. We've seen it generate current on an ammeter, and that's also ultimately by the dropped magnet went slower, though it's much less obvious to see how dropping a magnet is like a battery, and we'll have to kind of come back to that later. But it is ultimately due to the same effect. Now, to really actually get what's going on here, we really need to be more precise. And what do we mean by saying a changing magnetic field? And to do that, we have to talk about magnetic flux, because that's really what's going to be going on here. Now, magnetic flux is similar to electric flux we talked about with Gauss's law. And magnetic flux is, rough version, is how many field lines pass through an area. Okay, so if I have a loop of wire, for example, I have some area on the inside of that loop, and I talk about how many magnetic field lines pass through there. Now this picture is good for figuring out whether or not there is a change in magnetic flux, which we're going to try to get to in a bit. And to see if there's a change in magnetic flux, you just have to see is there a number of lines that pass through that area changing or not. We're going to give a number that indicates how many lines flow in, and it's going to be positive for one direction and negative for the other direction. So that if as many lines flowed in one way as out the other way, kind of out versus in, then overall the flux would be zero. So here's a better version of what's going on with magnetic induction. The better way of saying it is that changing the flux through an area creates an EMF on the edge of that area. Okay? So if I change, let's go back here. If I change the number of field lines that pass through some area, say this is a wire, it's like putting a battery along this edge. It's like making this into putting a battery along here. And the EMF describes the voltage of a battery. Now, it turns out there actually doesn't have to be a wire there, but if there isn't a wire, current's not going to run. It's too difficult to have current run through the air, for example. If you have a conducting material there and you put a battery in, then you get current.